In this video, I'm gonna solve the the uh, the problems in 4.9 and 4.10. So we'll see two problems. So a problem in 4.9 and the other problem in 4.10. So the first problem is this. The 1/5 kilogram mass is attached to a spring with a stiffness is 25 Newton per meter. And then the damping constant for the system is 4 Newton a second per meter. So from here, so we see a mass is 1/5, and then K spring constant is a 25, and then damping constant B is 4, right? And then if the mass is moved 4/3 meter to the left, so it means that the left of the equilibrium, so it means the initial position of the object is -4/3 meter. And then given an initial rightward velocity of 25 of 3 meter per second, so that's the second initial condition, right? So y prime of 0 must be 25/3. And then determine the equation of motion of the mass, and then give its damping factor, and then the quasi period and the quasi frequency. All right, so give me a second. Yep. So here, now we see that we start from the differential equation, the problem. So that definitely we should start from the second order, right? The linear ODE. So here the m is what? M is the, let's see, m is the 1/5, right? And then k is 25, and then b is 4. Okay, and then y of 0 is -4/3, and then y prime 0, which is initial condition, initial velocity, is the 25/3. Okay, so then and then the problem doesn't mention about the external force, so f of t must be 0 function. Okay, so and then put these numbers into the parameters, so we're going to get the 1/5 and then y dot prime, and then plus 4y prime plus 25y is equal to 0. Okay, so see right now. Okay, so now let me describe the what problem let me describe the problems. So here, let's say this is, for example, ground. Okay, so maybe raise the ceiling right there. Okay, so and the spring is attached right there. Okay, so let's say here's the objects are right here. Okay, maybe with the wheel. Okay, and then the problem says that what the mass is moved forward 3 meters to the left of equilibrium position. So if it right there here, let's say if we say this is the position of equilibrium. Okay, and then the position of the mass, initial position of mass, is going to be -4/3. It makes sense. Okay, right. And then the mass m is 1/5. Okay, so now then, so the spring constant k is 25. Okay, and then the damping constant can be 4. B is 4. Okay. All right. So then now we know how to solve this one. This is nothing but homogeneous, the second order homogeneous differential equation, right? So then we have to find the Ox equation first. So the Ox equation going to be 1 over 5 r squared plus 4r plus 25 equals 0. So then r squared is equal to plus 20r plus what? Excuse me. 125 is equal to 0, right? So then r going to be what? Negative what? The 20 plus minus the square root, the b squared, which is 400, right? Minus 4ac. Let's say 500, right? Okay, over 2a, which is 2. Okay. So since the discriminant d is negative, right? 400 minus 500, so it's negative. So we expect that this homogeneous differential equation will have the what? Uh, I mean, this Ox equation will have the two complex root, so that the homogeneous the general solution of this homogeneous equation should involve the sine and cosine with exponential term, right? So anyway, so let me figure out the root of the complex root of that Ox equation. So it's going to be negative 10, right? Plus minus, and then what about the square root of square root of 100i over 2, which is the see 5i. Does it make sense? Okay. So I mean, you got it right. So square root of 100 and the I over 2. This is equal to 10i over 2. So which is 5i, right? Okay. So this is alpha and then this is beta, right? Okay. So the general solution y of t is equal to c1 times, right, the e to the alpha t, negative 10t, and then cosine beta t, 5t, and then plus c2 times e to the negative 10t, and then sine 5t. Is it? Okay. So, but the let me let me find out the phase amplitude form of the general solution. So this is going to be a times, right, e to the negative 10t, and then sine, right, and then beta t plus phase angle pi, right? So okay. So we find out the amplitude and then phase angle, right? So then beta is what? Beta is 5, right? This is beta is 5. Okay. Then a is the square root of the c1 squared plus c2 squared, isn't it? Okay. So which is the what? C1. Yeah, definitely we have to find out c1 and c2. Okay. So we find out, and the phase angle pi is what? Pi is the arctangent of c1 over c2, right? Okay. So now here, what? The a times e to the negative 10t, okay? That is called the exponential damping factor, okay? And then this is called the sine factor, okay? But anyway, let's find out C1 and C2, okay? So the C1 going to be here, to find out C1, we need to impose the initial condition, right? So the y of 0, okay? So I'm going to substitute 0 into the general solution, okay? Okay. So then we're going to get the, I'm not going to plug in, I'm not going to use the phase amplitude form to figure out C1 and C2. Okay. So I'll use the kind of original, the general form of the general solution to find the C1 and C2. So y of 0 going to be what? C1 times, because the E2 is 0, 1. So cosine 0 and then plus C2 times sine 0, right? So since cosine 0, 0 and the cosine 0, 1, so we got the C1. That must be equal to what? Negative 4 over 3. negative 4 over 3. Okay. Then what about the the C2? So we use the initial velocity. Y prime 0 is 25 over 3. So to use that, we got to find out the derivative y. So y prime of t is equal to, see, we use the product rule, right, for derivative. So y prime going to be negative 10 times c1 times e to the negative 10t, and then cosine 5t, okay, the negative 5, and the c1 e to the negative 10t, and then sine 5t. The plus the negative, not plus, should be negative, right? Negative 10 c2 e to the negative 10t, and then sine 5t, okay, and then plus 5 c2 e to the negative 10t, and then cosine 5t. Okay, so now plugging 0 into t, then we got the all of the exponential term going to be 1. Okay, there's 1, so we ignore that. The cosine sine 0 is 0. Okay, 0 0. This is 1 1 1 1, and the cosine 0 is 1. Sine 0 0, and the cosine 0 is 1. I'm sorry, this is 1. Okay, so now then what? Which terms are left? So the first and then the last term are left, right? So we got negative 10 times c1, right, plus 5 times c2, is it? That, and then what is c1? c1 is a negative 4 over 3, right? So I'm going to plug in negative 4 over 3 into c1. So then, because c1 is negative 4 over 3, so we got negative 10 times the negative 4 over 3, okay? And then plus 5 times c2. That must be equal to what? 25 over 3, which is the initial velocity, okay? So then I'll solve this, that, the equation for c2. So let's solve this equation for c2. So 5 times c2 is equal to 25 over 3, and then minus 40 over 3, right? Okay, so this is equal to negative 15 over 3. Then c2 is equal to what? The one, negative 1, right? I'm sorry, not negative 1. Wait a second. Negative 1, right? Okay. So now so we got this so far. Back to here. So right here. So c1 is what? C1 is the negative 4 over 3. C2 is negative 1, right? So c1 is negative 4 over 3, and the c2 is negative 1. Okay. So then a gonna be what? That's gonna be square root of 16 over 9 plus 1, right? So which is the square root over see 25 over 9, which is 5 over 3. Okay, that's a. Then what about the phase angle pi? So here phase angle pi is determined by sine of c1 and c2, right? This is a c1, this is c2. Okay, so if the c1 sine of c1 is negative and sine of c2 is negative, so the pi, the angle, phase angle pi must be between what, 3 pi over 2 to 2 pi, or negative pi over 2 to 0. Okay, like this or like that. Okay, so because c1 is negative and c2 is negative side, right? So now then pi, so here the pi is what? The pi is equal to arctangent over C1 over C1 over C2 is a negative 4 over 3 over negative 1, which is what? Arctangent over of the 4 over 3, right? Okay. So we compute this what? Okay. Let me use a calculator. Okay. Yeah, so now here here we see, let's find out the arctangent 4 over 3. By the way, so here, sorry, but I made a mistake right here. So C1, I mean page angle pi should be third quadrant, not fourth quadrant, because C1 is negative and the C2 is negative. Okay, sorry, not right here, but right there. Okay, so in this one, in this region. So then when you calculate the arctangent 4 over 3 using calculator, so then see arctangent and then 4 divided by 3, then you'll get the 0.927295. So okay, so this is approximately 0.9273. Okay, so but here this one is that number is between this one belong to first quadrant, so we have to add what pi. Okay, so plus, then plus pi. Okay, and then plus pi, and then plus pi. So this is phase angle. Okay, so now then because arctangent, what's the graph of arctangent? Graph of arctangent is the graph of arctangent is like this. So, and then between negative, I mean between negative power over 2 to power 2, this is range of the arctangent. Okay, so the forward what negative, so negative 4 over 3. Give me a second. See 4 over 3 is right there. I'm sorry, 4 over 3, maybe 4 over 3 right there. So that will give the angle between 0 to 2 pi over 2. But as you can see, the phase angle must be in the third quadrant. That's why I add a pi. Okay, so we see that here. Let's say point in a C1, C2 coordinate system. 0.9273 is, for example, right there. Base angle, let's say this is the 0.9273 here. If we just add a pi, then we get the angle, which is the skew symmetric to that point, right? So this angle must be what? That angle must be 0.9273 plus pi. Okay. So anyway, so but the thing is that this the problem doesn't ask you to find the phase angle. The question is to determine the equation motion of the mass and damping factor, quasi period, and the quasi frequency. So yeah, fortunately, yeah, you didn't have to find out the phase angle, but I'm sure that this will help you to find out the phase amplitude form of the equation of motion in other problem. So, I'm sorry. So now back to the question. What's the question? Yeah, I told you equation of motion. So yeah, so this is the so the answer for the equation of motion. Okay, just plug in negative 4 over 3 and then negative 1 into C1 and C2 respectively. Okay, and then the damping factor is what? A times e to negative 10t. That's the damping factor. And then quasi period and the quasi frequency. What's the quasi period? So since you see that the general solution, the phase amplitude form of the general solution involve the wave function. So the behavioral solution is wave oscillatory, right? But because of the exponential term, the amplitude will decrease exponentially. So graph must be roughly is like this. Okay, so so there is no the period and the frequency can be applied here, but we can roughly we can figure out the period. We can find a period, quasi period, and a quasi frequency. Okay, so quasi period, that's the let me say P, okay, is the is a 2 pi over beta, okay, and then the quasi frequency is the what 1 over P. Okay, keep in mind this. So the what's the 2 pi over beta? Here the problem, in the problem, the beta is what? 5, right? So quasi period is what? 2 pi over 5. Okay, and then quasi frequency is what? 5 over 2 pi. Okay, so that's answer. So I hope that this problems help you to work the online homework. Okay, so then let's move to next problem. All right, next problem is the in 4.10. So 2 kilogram mass is attached to spring hanging from the ceiling, thereby causing the spring to stretch 0.245 meter upon coming to rest at equilibrium. At time t equals 0, an external force of F of t is cosine 6 of t Newton is applied to the system. So then the damping constant for the system is 1 Newton second per meter. Determine the state solution for the system. So as you can see that the mass is attached to spring hanging from the ceiling. So and the mass is 2 kilogram. And then so once since once the spring is attached to the spring, then the spring will be elongated from the equilibrium position. So the length elongated is 0.245 meter. And then at time t equals 0, external force is cosine of 60 Newton. So that's the external force. So we're going to deal with the non-homogeneous differential equation, right? And the damping constant is 1 Newton second per meter. So determine the state solution. So what's the steady state solution? That's the particular solution. Okay, we can find out the particular solution using the undetermined coefficient method of undetermined coefficient. Okay, all right. So here, okay. So give me a second. So what I do? So we start from the what m differential equation. I mean, this is 4.10.9, right? So my dou prime plus ky b, right? by prime plus c k y equals 0. So yeah, this is not equal 0. I'm sorry. This is the external force, which is cosine 6t. Okay. All right. So we need to figure out mbk, right? So m is the problem says that 2 kilogram, right? And then b is the 1 Newton second per meter, right? The k. So here's the problem. The problem doesn't give us the information about. I mean, doesn't give us the k. So we need to figure out k. Okay. So how can I find out k? So look at this. At the in the section 1, chapter 4, we so this figure, 3 cases. Case 1, case 2, right? So case 1 is the ceiling right there. Okay. And the case 1, case 2, and the case 3. And for the mass spring system, case 1 is just the spring is attached the ceiling. Okay. So then in this case, the tip of the spring, that is the called the equilibrium position, right? Okay, equilibrium position, right? But in case 2, once we attach the object, then definitely spring will be the elongated right here. So the mass right there. So the difference between the what the length, I mean elongated from the equation, let's say this is L, okay? All right. And then the case 3 is the not only the mass is attached, but also external force is applied. Okay. All right. So now, now in this problem, we apply the second case. Okay. For the second case, let's figure out what kind of forces acting on that object. Okay, definitely we have to consider the gravitational force Fg. Okay, and then also the spring force Fs. Okay, so now since the external force we this what in this state external force is not applied the object yet, so the mass, this mass will not be vibrated. Okay, so here we get the steady state. It means that Fs must be equal to Fg. I mean absolute value of Fs must be equal to absolute value of Fg. Okay, definitely the direction of the Fg is downward and the direction of Fs is upward, right? But the absolute value of these two guys equal, so that the mass not gonna we don't see any motion of the object. So now Fs is what spring force is. We are applying the Hooke's law. This is going to be k times, the spring constant k times the length elongated, right? That must be equal to gravitational force is m times g, right? Okay. So now from here, then what? K, we're going to get the equation for the k. K is what? K is equal to m times g over L. Okay. So what is m? M is a problem says that not a 2, right? 2. And then g is what? Normally 9.8 Newton per, the 9.8, right? And over length is what? The problem says that length is the 0.245. 0.245. Okay. So using the calculator, let's see, this is going to be 2 times 9.8, then divide by 0.245. That's going to be 80. So this is 80. Okay. So we got we figured out the spring constant. And now, okay, so right here, next, so we got this 2y double prime, and then plus y prime, and then plus 80y is equal to cosine 60. Okay, now let's find out the particular solution using the method of undetermined equation. Then yp of t is equal to, so since the external force involve the cosine functions. So basically the form of the particular solution must be what? T to the s power, and then a m. Let me see. Because if we use the letter m for the mass, let me use other letter. Let's say n. A n t to the n's power plus through the a0, right? And then e to the alpha t, and then cosine beta t. This is a plus t to the s power, and then b there's an n prime, okay, and then t to the n prime plus through the b0, and then e to the alpha t, and then cosine sine beta t. Oops, sorry, sine beta t. Okay, but let's ignore the e to the alpha t because what because the external force doesn't have the external exponential term. Okay. And also, the external force doesn't is not involved the polynomial function. So all these terms in a polynomial will be ignored. Okay. So now then we got this what, and then we need to figure out the s and the beta, right? So beta must be 6, right? So here beta must be 6, and the alpha must be 0, by the way. Okay. And then what about s? we need to figure out S, we have to find out what? The root of Ox equation, right? Okay. Then Ox equation is going to be what? 2 times R squared plus R plus 80 equals 0. Okay. Then R going to be negative B plus minus square root B squared minus 4AC. 640, right? Over 2A. Okay. But so definitely in this one, I mean, so this is equal to negative 1/4, right? And then plus minus the square root of 639 and then times I, right? So this is the image real part. This is the image part. We're going to compare the what? Alpha and then real part and then beta in the image part. Definitely, this complex root is not matched with the alpha plus beta I. So in that case, S must be 0. Okay, the S equals 0. Okay. So because alpha plus beta I is not equal to negative 1/4, and then plus square root 639 I. Okay. All right. So now then YPT, okay, the form of the particular solution will be reduced by well, A0 and then cosine, the beta is 6, right? 6t plus, okay, so plus, and then B0 times sine beta t, which is 6t. Okay. Okay. So now we plug in to find the A0, B0. Okay. Plug in A0, B0. To find the A0, B0, we use we need to plug in this one into the differential equation. Then we need to figure out the YP prime t. Also, we need to figure out YP dou prime t. Okay. All right. So, and then plug in these three YP, YP prime, YP dou prime into the differential equation. Okay, and then compare the left-hand side, the right-hand side. We can figure out A0, B0. Okay, so let's see. Excuse me. So YP prime is a 6 times A0 minus, and then sine 60, right? And then plus 6 times B0, and then cosine 60, right? The YP dou prime is what? Negative 36 A0, okay? And then cosine 60 plus 36 minus B0 sine 60. Okay. And then now, right there. Okay. Then let's see. Then 2 y dou prime, I mean 2 yp dou prime plus yp prime plus 80 yp, that is equal to, okay. First one, I want to just declassify cosine term and sine term. Okay. So then we'll see, we're going to get the first one. Let me figure out the coefficient term of the sine term. Okay. Then let's see, 72, right? 72 B0, and then plus 6 B0. Oh, minus 6 A0. Okay, and then plus 80 B0. Okay, that's the coefficient term of the sine term, sine 60. Okay, and then plus the coefficient term of the cosine term going to be negative 72 A0, and then plus 6 B0. Okay, and then plus 80 A0. the cosine 60. Okay, so now then what? The 72b0 minus 6a0 plus 80b0 must be 0, and then this one must be 1 because the what? Because the external force is cosine of 60, right? So we got this 72b0 minus, 6a0 plus 80b0 is equal to 0, and then negative 72a0, and then plus 6b0, and then plus 80a0 is equal to 1. Okay, so, and to simplify the left-hand side for each equations, then we're going to get the negative 6a0, and then plus 152b0 is equal to 0, right? And then let me see, 8a0 plus 6b0 is equal to 1. Okay, so we see. Now let me see. Then let me solve this one. So then give me a second. Then a0. Let me solve the second equation for a0. Then a0 gonna be 1 minus 6b0 over 8, right? So plug in this one into the a0 in the first equation. We got the negative 6 plus 36b0 over 8, right? Plus 152b0 equals 0, right? So we got the negative 6 plus 36b0 plus 8 times 152 is what? So we got 1216. Okay, 1216 b0 equals 0. So let me see. So we got let me see. We got 1 b0 gonna be 6 divided by, right? 1 1 2 5 2. Okay. Then a0 gonna be what? 1 minus 6b. So 1 minus, see, 1 minus 6 times 6 divided by 1252. Okay. Okay, and then divided by 8. So let me but I got the decimal expression, but I want to get the rational expression. So let me do by hand. So we got, see, 1 minus 6 times 6 over 1252 over 8. So this is equal to 1 minus 36 divided by 1252 over 8. Then this is equal to minus 35 over 8 times 1252. Okay. So then 8 times, yeah, so can you see? You see that 8 times, this is a0, this is b0. Okay, so we figured out the particular solution. Okay, so put these two a0, b0 into right here, a0, b0, right here. Okay, I don't think you have to convert this one to the phase amplitude form. Okay, so this is the problem in 4.10. Okay, but by the way, but what you can use the give me a second. So in the when I covered the 4.10, so actually I gave you the formula of the particular solution of that kind of non-homogeneous differential equation. Mass spring system with forced mechanical vibration. So you can use this one, but I recommend you to do it like this, so that even even if you just forget about the formula, so you can solve the problems. Okay, so let me stop here.